So welcome everyone to our Master Seminar Series. Today we have Professor Salil Vadhan, who's the Vicky Joseph Professor of Computer Science and Applied Mathematics at the Harvard John Kaufman School of Engineering and Applied Sciences, and the Faculty Director of the OpenDP Open Source Software Project. He is currently visiting the University of Sydney and hosted by Clement. So Professor Salil Vadhan's research is in theoretical computer science, and it spans computational complexity, data privacy. His honors include the Harvard College Professorship, the Simons Investigative Award, and the Guggenheim Fellowship. Welcome, and the floor is yours. Thank you.
Thank you, Jana. Sorry for. It doesn't seem like I'm being caught on the camera. That's why I'm trying to move this direction. So, dangerous cord. Now I can see myself on the. All right. Hello, everyone. I'll be telling you kind of a long journey, both partly a personal one, but also about the field of differential privacy, going from theory to practice and back. Some of it will be fast because I want to tell this long story, but I'll try to kind of slow down for the more technical parts. Let's see. But let me begin with this acknowledgement. It's a very nice thing that you all do here in Australia. I wish we did more of it in the US. So I would like to acknowledge the traditional owners of Australia and recognize their continuing connection to land, water, and culture. I am currently on the land of the Gadigal people of the Eora Nation and pay my respects to their elders, past, present, and emerging. And for those of you on Zoom, I further acknowledge the traditional owners of the country on which you are on and pay respects to their elders, past, present, and future. And now for a second acknowledgement, I would like to thank everyone, particularly Clement, Joachim, and Willie, for making possible this really delightful visit to the University of Sydney. It's been great in many ways. I'm showing one of my favorite beaches here, Curl Beach in the background, but also scientifically, the community here has been very stimulating. And also want to thank very much the staff as well, who helped make my visit possible, especially Priyanka, Will, and Greg, who rescued my laptop at the end of last week. Otherwise, I might not be able to give this talk at this moment. And all those who worked on my appointment in HR, and in general, the community of faculty, staff, and researchers. Great traditions of you all going out to lunch together regularly, things that I want to bring back when I go back to the US. And I'm looking forward to my next visit. I hope this one felt too short, and hope it's the first of many. All right, so I will begin with a very sort of quick overview of differential privacy, and to set up some of the concepts that will come up again later in the talk. So differential privacy aims to enable statistical analysis of sensitive data sets while providing strong guarantees of protection to the individuals in those data sets. What we mean by, let me talk a little bit about what we mean by utility. So statistical analysis, what does that include? That includes doing releases of statistical publications like statistical tables published by national statistical offices. It includes also the parameters of trained machine learning models, as well as producing synthetic data sets, something that will come up again later in the talk. It also includes query systems where you don't make a one-shot publication on a data set, but analysts who want to analyze the data can issue queries of their choice. For example, give me a regression on a particular set of variables and get answers. And somehow differential privacy is the mechanism here, the interface is supposed to ensure that we can provide useful answers, but not compromise the private sensitive information in the data set. All right, and there's lots of examples of these. These are from government agencies in the US, Census Bureau, education statistics, genomic data, as well as from tech companies, Google search trends that are examples of kind of statistical query interfaces like this that are in the scope of differential privacy. Why do we need a new or relatively new methodology and framework for protecting privacy in these sorts of statistical settings? Well, it's because the traditional methods for protecting privacy and sensitive data are now well understood to be ineffective and often breakable. So the most basic method is removing so-called personally identifying information from a data set, strip obvious identifiers, and hope that the data set that remains is anonymous and therefore no longer has privacy concerns. But it's been repeatedly shown that such data sets can often be re-identified, sometimes by making use of other externally publicly available data sets to figure out who's who from the information that was there in the data set. Perhaps more surprisingly and directly related to differential privacy, it was discovered, starting in the seminal work of Dinur and Nissim, that even what appear to be only aggregate statistics can have very serious privacy concerns. And so Dinur and Nissim showed the possibility of what are called database reconstruction attacks, where you can take many published aggregate statistics, each of which on their own seem like they're not problematic. They're aggregates over large subpopulations, and combine them to reconstruct almost all of the underlying sensitive data. This was shown in theory by Dinur and Nissim, but then applied in practice, for example, by the US Census Bureau, which motivated and shown that the billions of numbers that they publish in the tables based on the every 10-year census in the US actually is enough to carry out these kind of reconstruction attacks. Okay, and there's also things called membership inference attacks that have been shown to be a concern in genomic statistical publications, like the web interface I showed earlier, and machine learning services produced by the tech industry. And these kinds of privacy concerns have become really, in the machine learning context, have become really visceral with generative AI, where it's been shown even with earlier models like GPT-2, even though they're trying to learn generalizable models of language, for example, being trained over a large corpus of training data, they inadvertently memorize some of their training data, and this can be extracted by putting in carefully constructed prompts into the systems, right? And so these are really serious privacy concerns. Okay, so now let me talk a little bit about how differential privacy captures the idea of what it means to protect individual level data. So we want to enable analysis of populations, statistical analysis, while making sure that information about specific individuals isn't compromised. And we want to, in differential privacy, we want to do so without anticipating what attack strategy an adversary might use and what background information, what auxiliary data sets they might bring to bear as they attack the system. Okay, so what differential privacy at an intuitive level requires is that those interacting with the system and getting its outputs, to them, the effect of each individual data subject should be hidden in a precise sense. All right, each individual person in the original data set. So what we imagine is an adversary interacting with the system, potentially issuing adversarial queries, and consider any one person in the original data. I don't know why the adversary turned into the data set. Sorry, that should still be an adversary there. Not sure how that happened on the right side. Imagine any one individual in the data set that the adversary might be trying to learn something about, and imagine erasing their data from the data set. Right? And then differential privacy requires that the adversary shouldn't be able to tell the difference from what they see in the real world when that person's in the data set to a hypothetical if we remove that person's data from the data set, or potentially replaced it with arbitrary other values. And this is supposed to hold simultaneously for all the individuals in the data set, and no matter what your data set is in a worst case sense. So it's a very strong notion of privacy. How is this achieved? It's achieved by the introduction of random noise into the computations. And so the most basic example is, suppose I have a query that's doing a count or a population proportion. What fraction of people in this data set have some property, say blood type B, and are HIV positive, have a particular disease. Okay, and so a standard way to achieve a differential privacy is just to take the true answer and add a small amount of random noise from an appropriate distribution to the true result. Okay, so why does this intuitively satisfy the requirement we want? Well, let's think of what's the influence of any one person on the true answer. Since we're doing a fraction over a data set of size n here, any one data subject can influence this true answer. Any one row, it affects it by at most plus or minus 1 over n. And so if we introduce noise intuitively that's of magnitude a little bit bigger than 1 over n, then we should be able to drown out the effect of each individual in the data set. Okay. And the point is, so the amount of noise we need to introduce kind of can vanish, like in this case of a population proportion, like 1 over n. And so, our true answer is a number between 0 and 1. And so as n goes to infinity, the noise we're introducing for privacy goes to 0. And in fact, goes to 0 more quickly than the statistical sampling error you might expect if this was a sample of a larger population, where you would expect an error of about 1 over square root of n. So at least asymptotically, in some sense, privacy is coming almost for free here. Okay, so let me be a little more precise now. So I noticed that I had this epsilon in here in the magnitude of noise, which is governing how much bigger than 1 over n I scale up my noise. And so that's saying differential privacy is not a binary, either you have differential privacy or not. It's a quantitative theory where you measure the level of privacy protection or privacy loss to the individuals in the data set. And that's governed here by this parameter epsilon. The smaller epsilon is the less privacy loss people in the data set are incurring from this release. And formally, what differential privacy requires is that for any pair of data sets, what we call adjacent data sets. So these are data sets that differ on one person's data. Right. In this example, it's differing on one row, because this is a data set where every row corresponds to a person. And every potential query that I issue, the probability distribution of outputs on one data set X and the adjacent data set X prime should be close to each other. Okay, should be kind of indistinguishable from each other at a level that's governed by this parameter epsilon. Okay, and this is the kind of definition that gives that strong guarantee that gives protection regardless of what other auxiliary information an attacker might have or what computational strategy they might carry out. Right? We require that these are closest probability distributions. Yes.
So intuitively, the claim seems right. Yeah, I mean, if these two data sets are indistinguishable to you, the attacker, and they differ on any one of, then okay. But it sounded like they were quite sophisticated attacks for other non-DP approaches. So is there a formal argument?
Yeah.
This is actually, I mean, there must be some adversarial model which this doesn't defend against. I mean, presumably. I mean, what's really?
So what I mean by attack strategies is a great question. So the question for those on Zoom, do they hear the questions that are asked in the room, or do I have to repeat them?
I think they would be.
They were Mike. Okay, great. So what I mean here, so this differential privacy has what's called a so first a post-processing property, no matter how you take what's computed on these outputs, right? Right now, I've only talked about answering one statistic, but in general, no matter how an attacker takes what they computes on it, it's still going to be differentially private. And one can quantitatively relate it to the kind of attacks that I talked about earlier, reconstruction attacks and membership inference attacks. You can say epsilon will, in some sense, bound how well one can do any of these kinds of attacks, right? And epsilon, when epsilon goes to 0, these attacks are completely kind of useless, failing. Now there is something that's important here. I said the attacker can have other data that's available, but it's not protecting against an attacker that, for example, gets to observe the randomness introduced by the mechanism. So there is that implicit assumption that the randomization is secret here. Okay, and so the randomness, just like in cryptography, the randomness is a source of protection. And there's other side channels that you might worry about. Zach, my graduate student who's visiting, is working on timing attacks against differential privacy and how to defend them. Sometimes, here we're assuming you only see the output from the mechanism. Well, what if you can measure how much time it takes? Well, that's another attack vector. It's leaking information that's not captured in the basic model, right? But subject to having the model of what the adversary can see, one can actually connect.
So for instance, if you're allowed to repeatedly make the same query, so it'd be essentially you're sampling the noise now.
Great.
This would allow you to potentially learn the noise, which is something you said we want to keep hidden.
Great point, and I will come back to that, and I'll come back to that in a moment. And that relates to this is just an example for a system that's designed to answer one query and then shut off. What you're getting at is, I talked about these query systems. What if, we wanted to offer systems where people can issue multiple queries? So first, what's the definition of privacy for that case? So it becomes a little more than saying for every query, the probability distributions are close. What we really should say, and this is going to come back again in some of the research problems I'll talk about at the end of the talk, we should quantify overall adversarial strategies, that it's all attackers interacting with a system that potentially adaptively are choosing what query to ask based on what it's seen. And what we should ask to be close are what's called the view in cryptographic language of the adversary, which is basically the transcript of everything the adversary sees. That's a kind of random variable over the randomness introduced by the mechanism on data set X versus on data set X prime, the adjacent data set where one person's data is removed. All right, and then there's even more complicated settings if you're talking about streaming data coming online, and so on. But let me not get more involved than this. And I will, Sasha, I still haven't answered your question. I will in a moment. Just want to say, most of you have probably seen, if you've seen talks on differential privacy, just this more basic definition where there's no query that's explicit. And there's no adversaries, no interaction, adversarial strategy. This is what we call basic non-interactive differential privacy. We just have a mechanism that takes the data set and is producing a release. And then this is the typical way in which closeness between the distributions is captured in a multiplicative sense. We require that the probability distribution on data set X is multiplicatively close within a multiplicative factor that's close to 1. That's this e to the epsilon, to the probability distribution on X prime. All right. At a high level, the way to think about differential, a generalization that's useful to think about is differential privacy requires that adjacent data sets, ones that differ on one individual's data, get mapped to close distributions, close probability distributions of outputs. And again, what will come up later in the talk is the literature has produced many ways of measuring closeness between probability distributions that are useful for reasoning about differential privacy, capture more information than this one number epsilon that's in the most basic definition of differential privacy. Sometimes you use two parameters, a multiplicative epsilon and an additive delta. Sometimes we use these Renyi divergences. If you've heard of what those are generalizations of KL divergence from information theory. And sometimes there's another formulation, FDP, that uses the hypothesis testing viewpoint of differential privacy, where the adversary is trying to do the hypothesis test on is it data set X or X prime. Okay. So that's just a kind of a preview for, again, things that will come later. We won't need any of the formal definitions for what I'm going to talk about, just to give you a taste of kinds of questions. All right, so now I said differential privacy is quantitative theory, so it accepts that any statistical release you make on data incurs some privacy loss for the individuals in that data set. Okay, and the more noise you introduce, you can provide a higher level of privacy protection, but you're getting less accurate statistics out. Conversely, less noise you introduce, you provide weaker privacy protections, but you have more accurate statistics. And as I said earlier, this trade-off becomes less stark as your population size grows. It does better than sampling error, for example. Now, to Sasha's question, what if you want to answer multiple queries? Well, differential privacy has nice composition theorems that tell you how privacy loss accumulates when you answer multiple questions. In the basic measure of the most basic composition, you can upper bound the privacy loss by the sum of the privacy losses on the individual queries. Okay, and but there are more sophisticated composition theorems for differential privacy, and that's actually most of the motivation for those more sophisticated measures of distribution closeness that are used in the differential privacy literature is to reason more tightly about how privacy loss degrades when you do many differentially private algorithms. And now, again, to Sasha's question, the recommended use of differential privacy is to set a budget to say this is how much privacy loss we are willing to take on the subjects in our data set. This is kind of acceptable given their consent and what the data is being used for, and ensure that you stay in that budget using these composition theorems, which means that if you want to answer more and more queries, you must introduce more and more noise to stay within the budget, and eventually you're producing answers that are completely useless. All right, and so if you keep asking the same question over and over, either you're going to be getting noisy and noisier answers, or the system at some point is going to say, sorry, I'm done. We've reached the privacy loss budget on this data set. Okay, so this is from 10 years ago, and then I gave up on keeping track of how the differential privacy literature was exploding, but kind of virtually everything that we do in statistical data analysis, in data science and machine learning has been studied and shown, at least in theory, to be compatible with the privacy protections of differential privacy, kind of with good behavior as kind of your population sizes and at least asymptotic behavior, though there are many challenges that remain in making these methods effective in practice. I also want to say that many of these introduce noise in more sophisticated ways than what we showed in the simple example. It's not just you do your standard non-private thing and add noise at the end, but introduce noise in clever ways in the middle of the computation, and sometimes not just in a kind of adding noise sort of fashion like we showed. Okay, so let me just tell one sort of thing that was kind of an amazing possibility shown in the very early days of differential privacy by Blum, Liggett, and Roth. They showed that, in principle, it's possible to generate very rich synthetic data while satisfying the protections of differential privacy. All right, so suppose I have a data set with n people in it, d attributes, where d is quite a bit smaller than n, but can still be, say like square root of n. And we want a differentially private algorithm that produces a synthetic data set, so it has the same schema as the original data set, but these are not people that have just been taken from the original data and de-identified, right? They're each synthetically generated, so no one-to-one corresponds with the original data set, so that it still retains a lot of the statistical features of the original data. And what they showed is it's possible to do this as one example of their result in a way that approximately preserves, say, to within plus or minus 1%, plus or minus 1% of the data set size, the fraction of people in the data set with every possible combination of attributes. All right, so how many people in the data set are female and blood type B? How many people in the data set are blood type O and HIV positive? Every combination, not just pairs, triples. So there's exponentially many combinations of attributes, and simultaneously all of these are preserved in the synthetic data set. The problem was that their method uses computation time that's exponential in the number of dimensions. It's preserving exponentially many statistics, but it's computing also in time that's exponential. And so that was a natural way for me as a complexity theorist to get my foot in the door in this line of research and ask, is that really inherent? And so some of the first work that I did with collaborators on differential privacy and students of mine was understanding the computational complexity of differential privacy. And in fact, the synthetic data generation problem is inherently hard in the worst case. It requires exponential computing time unless all cryptography can be broken in sub-exponential time, which we strongly don't believe. Right? And this was kind of someone surprisingly managed to bring in fairly a rich set of tools from both cryptography and complexity theory, digital signatures together with probabilistically checkable proofs and other complexity machinery, if you've heard of those things. Okay. And so that's kind of leads to the this end of this first part of the talk, where I want to kind of just convey the point that from even just a purely theoretical research point of view, differential privacy turned out to be a goldmine. It raised fascinating questions and still does, connections for theorists in many areas of theoretical computer science, mathematics, statistics, programming languages. It seemed that anyone who came to this area had ways of bringing their toolkit to bear and bringing tools from differential privacy also back to their own research area. And there's many fundamental theoretical questions. So even though the rest of the talk will kind of be focused on practice and the questions that practice raises, there's even just things from a purely theoretical, like a intrinsic theoretical interest that deserve a lot of attention. All right, so now let me turn to the efforts to bring differential privacy to practice.
Still theoretical question. So your computational complexity applies to the current differential privacy definition, right? The current DP definition actually assume that adversary is like unbounded. This adversary could essentially have an information theoretic type. If we restrict that adversary, it could be also a computational setting. Would the computational complexity still apply?
Great question. Yes, I believe implicit in this negative result, maybe even explicit in our paper. I don't know, it was more than 10 years ago, so hard to remember for sure. The attacker is actually a polynomial time attacker as well. So it even and does more than just break the basic definition of DP, but even fairly substantial relaxations of it. But thanks. Okay, so how did I get involved in the practice of differential privacy? So we started an interdisciplinary research project at Harvard, the Privacy Tools Project, which brought computer scientists like me together with scholars from law and social science and statistics who were encountering privacy and thinking about privacy problems that seemed very much in line with the kinds of privacy problems that differential privacy wanted to tackle. And so we thought about questions about how does the mathematical definition of differential privacy relate to the normative way that law scholars are thinking about privacy, as well as how can the tools that we're developing in differential privacy potentially be used to enable social scientists to share their data more safely. And then within a couple of years, there was also really an explosion of deployments of differential privacy, first by big tech, Google, Apple, Microsoft, now all of the big tech companies doing large-scale deployments of differential privacy. Then the US Census Bureau making the landmark decision, as I mentioned earlier, to adopt differential privacy for all of the public use products from the 2020 decennial census in the US, and an emerging industry of startups and privacy consulting services that were incorporating differential privacy into their offerings in some way. Some kinds of uses of differential privacy, as an example of one that I think is a sort of very positive one, and kinds that we'd like to see more of, were where Google and Facebook during the pandemic made available dashboards about human mobility and economic activity in a differentially private way, so that policymakers and epidemiologists could see the effectiveness of lockdown policies and to what extent that was changing the way people behave. There also was an increase of open source software available for differential privacy. Some of it from big tech really focused on large scale machine learning. A lot of academic proof of concepts that were kind of mainly meant to accompany research papers, but not really being turned into production software. And some open source general purpose libraries where companies would put out whatever they had developed internally for their own use cases. But we felt that there was still a big gap in meeting the needs of the community. And so we launched this open source software project, OpenDP, started the effort in 2019, a community effort to build trustworthy open source software for statistical analysis of sensitive private data with the protections of differential privacy. And what we're trying to provide in OpenDP over the current landscape is a few things. So one is around trustworthiness. So as I will talk a little bit about later and hinted at kind of in some of the earlier discussion, implementing DP correctly so that the implementation actually provides the kinds of guarantees that are promised on paper with differential privacy is actually pretty challenging. And most efforts to date have gotten it wrong. And open source software is good for addressing those sorts of issues, but it's not enough for the software to be open source. You need really a community of people who are engaged in inspecting the software and vetting it for its promised properties. And we are building that process in OpenDP and getting the community engaged. Another is flexibility. So when we started OpenDP, most of the DP software you could find out there was built for a very bespoke use case and very tailored to that and hard to apply or adapt to new applications. And we really designed OpenDP with flexibility in mind to provide a foundation for lots of variety of applications and something that could really grow with the rapidly advancing science and practice of differential privacy. And finally, we feel like especially in this space of privacy, it's important to have a project and software that's really governed and owned by the community, rather than just relying on the goodwill of companies to put out there what they've developed for their own purposes. And the kinds of use cases that we're most interested in OpenDP are these first few, which really involve opening up sensitive data for scientific research and exploration in the public interest. So whether that's researchers sharing data sets with each other through data repositories, government agencies making data available to the public, or some of the examples I gave earlier, companies making data available through, for example, data for good programs. Our primary support, the largest portion comes from the Sloan Foundation and National Science Foundation with some other funders, and we've been collaborating very heavily with Microsoft on a particular toolkit called Smart Noise Toolkit, which is powered by OpenDP from the start of the project. And we're grateful for gifts from a number of companies as well. Joined by Gary King, a political scientist and applied statistician, in running OpenDP. This is our core team. Looks like a large team, but many people are only devoting a fraction of their time. Also grateful to all the students and interns and developers and other projects who've contributed. My student Zach shown there is here across the table. And we're grateful also to our advisory board, lots of thought leaders in data privacy and related areas, open source software, domain science, and research ethics, who provide us lots of guidance. Okay, so let me talk a little bit about the OpenDP software, which will lead to some of the research questions I want to end with. So the OpenDP software, sorry, this is a little bit small, is divided into two parts. This is the overall OpenDP ecosystem. The yellow part shown here is what we call the OpenDP Commons, and that's the portion we think of as really kind of owned and governed by the OpenDP community. And the heart of that is the OpenDP library, which I will talk in some more depth about shortly. But that's really where the implementations of the fundamentals of differential privacy and how DP is modeled in code exists. But we also think it's important, and I won't get to talk about today, that there's not just a library of differentially private algorithms that experts can make use of, but that there's actually also more user-friendly end-to-end systems, interfaces for using differential privacy. And we've worked on two of those. One is that smart noise toolkit that we've worked on with Microsoft. That's outside the Commons. That's something that kind of Microsoft and together with us are responsible, the core team is responsible for managing. And there's another tool, a graphical user interface that we've been developing for a number of years called DP Creator, which is part of the OpenDP Commons. And you can play with both of those by going to our GitHub repository or download the source for those tools, as well as the OpenDP library. We've had several production uses of OpenDP so far. Some are public data releases, nationwide data set about broadband usage in the United States released by Microsoft, hospital data on hospital stays during COVID-19 by Data Fleets and LiveRamp, public dashboards for evacuations after a hurricane by Cubic and Spectus, and then a number of more less public uses of OpenDP. And then we're working with a number of other partners on other deployments. Probably the biggest partner along those lines has been the Swiss Federal Statistical Office, and we have a number of projects underway with them. All right, so let me get to the OpenDP library. It's implemented in Rust. But there are bindings. It's now in version 0.9, bindings to use it from Python and R. As I talked about earlier, we really care about trustworthiness, because we want this to be something where, again, we're not just trusting the few developers, core developers, to do things right, but even to accept contributions from the external community. We want it to be something that grows through community contributions. And so we have, for each core component of the library, mathematical proofs that are attached to the code. And there's a vetting process by which the privacy properties that are asserted in the code are checked. It's checked that the proof actually validates those, and only through that do the things become part of the vetted part of the OpenDP library. Right, so that's the vision, and we're currently building. We've been doing this vetting process internally to, as we try to get the foundation of the library built. But now we are taking nominations for the proof review board that's being chaired by Marco Gabardi and Michael Hay. And kind of formalizing this process for the long term. Sasha.
What are these proofs of?
I will get to that shortly. Thank you. All right. So what are these proofs of? That's basically the OpenDP programming framework, which I developed with Marco Gabardi and Michael Hay, which has a number of, Desiderata. This is the kind of the framework for the implementation in the library. A couple of these have to do a lot with the flexibility, that we wanted to capture the many different ways that people were reasoning about privacy in the literature and different applications, different kinds of data sources. So you don't have to just talk about a tabular data set like I was talking about earlier, where individuals are rows, but you could talk about graph data, where social networks, where people are nodes in the graph, or data streams, where users might be associated with many events. Generality in the other ways we reason about privacy, like composition that I talked about earlier, but there's a number of other tools there. To Sasha's question, it's important that the framework provides and the implementation provides a clear specification for what are the privacy relevant properties of every component, so that we know what we're writing a proof of then when we attach proofs to the code. And then a final feature that relates to what I brought up in the beginning of the talk, we chose to make interactive DP algorithms as first-class citizens in this framework, and that raised some interesting new research questions. All right, and so the basic building blocks are things that are called measurements and transformations that I'll tell you about in a moment, and then we also have tools like composition methods, chaining that I'll give an example of, post-processing, other things that allow you to take these basic components and stitch them together to build more complex DP programs. All right, and the feature we want is that if you've proven the properties of the building blocks and you've proven the properties of these combinators, then you don't need to provide any new proof for the complex DP programs that you build out of them. It's kind of automatically derived or implied by the proofs of the components. Okay, so what are these basic building blocks? Measurements are what earlier in the talk I was calling mechanisms, and are typically called mechanisms in the DP literature. For historical reasons, measurements became the terminology. We might switch back to mechanisms. They are a generalization of this basic concept of DP that, the definition of DP says, if I have adjacent data sets or data sets that are close, they differ on one person's data, all right? Maybe they differ on a few persons' data. Close data sets go to close probability distributions of outputs, okay? As measured by like epsilon in epsilon differential privacy. And what a measurement is something where we allow generalizing this concept to essentially arbitrary notions of closeness. So you can have any way you want of measuring closeness between data or data sets, and essentially any way you want of measuring closeness between probability distributions, just subject to a kind of few niceness conditions. And we allow such a thing to be called a measurement. Okay, and so we already talked about the many ways people measure closeness between probability distributions. To talk about why it's useful to measure closeness between data in different ways, let's think of a very standard DP pipeline, which is actually like the example I gave earlier in the talk. So suppose I want to do a DP noisy sum, like count the number of people in the data set that are male and blood type O in the data set, right? It's an example like I had before. Okay, so you can break that down into a bunch of smaller steps, components, as follows. First, we take our data set, then we apply a predicate to every record to get a 0 or a 1 to tell you whether it satisfies the property you're interested in or not. Then we compute the sum, okay? And then we add noise to that sum. The reason I've broken it up this way is that it mirrors the way we prove the privacy properties of this DP algorithm. What we say when we prove the privacy properties is we say, suppose I have two data sets that are adjacent. They differ on one person's data. Well, then I will get, after applying the predicate to every row, I will still have two data sets that are close. They will differ on at most one person's data, because I've just operated, when I've turned each record into a 0 or 1, I've operated just record by record. Then I will get two sums out that are close, because if I have two data sets of bits that differ on one person's data, the sums will differ by at most plus or minus 1. Here I'm doing a sum rather than a fraction like I did earlier. And then if I add enough noise, I will get close probability distributions of outputs. Okay. So that's the concept of a transformation. Are these like first two steps where I take data that's close and I transform it in some way, close in some sense, and I transform it in some way to get new data elements. These could be data sets like after the first transformation, or they could be scalars like after the second transformation here, that are guaranteed to be close if the inputs were close, right? And they could be vectors. They could be, again, they could be graphs. You can have any way you want model in the OpenDP framework, any way you want to measure in closeness. Okay, and so the attributes of transformations and measurements, which are represented explicitly in the code, they have the functions that they actually compute, right? So transformations are typically deterministic functions, though they can be randomized. Measurements are always randomized functions. And then you have your, the domain, which might include information, includes data types, but also information about like whether the values are bounded. So, after applying this predicate to every row, later I use the fact that the values are between 0 and 1, right? They're not unbounded values to say that the sums will be close. The metric, how are you measuring closeness? It doesn't even need to be a metric in the usual math sense. You can measure not just by a single number, for example. And the metric for how you're measuring closeness on the output, or how you're measuring closeness between probability distributions in the case of a measurement. Right. So these are the things. And then there's a stability map and a privacy map, which tell you, you put in an input distance, say how many rows do these two data sets differ on, and then you get an output distance out. How much can the result of the transformation, how much can the sums differ by? Right. And so these privacy maps are also explicitly, or stability maps for transformations are explicitly represented in code. And these are the things that one is giving proofs of to Sasha's question. The mathematical proofs assert that the transformation or measurement actually has the stability property that's guaranteed by its stability or map or privacy map. All right. So trying to be really careful about this and breaking things down into very simple components, we realized even things that we take for granted in the DP literature, like this summation operation, actually, when you implement it in the first way that you would try, it actually fails to have the stability properties that you thought it had when you reasoned about sums on paper. And it fails for finite precision arithmetic. In the case of floating point numbers, that's because of round-off errors. In the case of finite precision integer arithmetic, it's because of overflow. And it can actually lead to quite dramatic violations of differential privacy. So that led to a fun research, an interesting research project done with our two wonderful undergrad interns, Silvia Cascoberta and Connor Wagaman, where we found that this failure to meet the differential privacy was out there in essentially all implementations of differential privacy, failing to reconcile for the way that arithmetic on numerical data types is not the same as arithmetic on idealized real numbers that we write research papers about. All right, so that's one example of theory to practice to back to theory. Those were theory questions that came out of the implementation, really kind of like numerical analysis type ones. And let me tell you about one more that relates to this concept of making interactive mechanisms a first-class citizen. So recall that I said in the beginning, and more recently we worked with this more general notion of like a differentially private interface to the data where you can adaptively ask queries. In code, in the OpenDP library, we represent this as a randomized state machine. It turns out to be the right useful programming implementation of this idea. And we have this way of requiring the privacy property that the view of the adversary for every adversary strategy, the views should be close on adjacent data sets, all right, measured by epsilon or epsilon and delta or whatever your measure of closeness of probability distributions, right? And this additional quantifier over all adversary strategies that's not present in the basic non-interactive definition of DP is what makes this kind of more subtle and challenging to work with. But nevertheless, it's very useful if we can, because actually a number of things that are basic building blocks in the DP literature are actually best modeled as interactive stateful procedures like this. And some of them do actually maintain state, things like the sparse vector technique, if you've heard of that in the differential privacy literature. All right, so they're not just independently adding noise to answering queries and tracking a budget. They're actually maintaining some non-trivial correlation in the way they answer queries. All right. And so the question, we realized once we decided to make this a first-class citizen, we realized we didn't actually know whether the existing composition theorems for DP extend to interactive mechanisms. Somehow, the literature never asked this question. Okay. So, all right, what was fairly straightforward, what is it to handle was what's called sequential composition, where here I have, say, K interactive DP mechanisms. The adversary or analyst gets to interact with the first one and has to finish before it starts interacting with the second one, and then it can interact with the third and so on. That's called sequential composition. And fairly straightforward to extend the proofs of existing composition theorems for non-interactive differential privacy to the setting for interactive. More natural way, though, once you're working with interactive DP to allow for interaction with the mechanisms is to allow an analyst or an adversary to arbitrarily interleave its queries. It first can ask a question of the first one, then of the second one, then go back and ask a question of the first one, and so on. And here, composition is much more subtle. And in fact, in the cryptography literature, there are classic examples showing that for other kinds of things in cryptography, concurrent composition provably invalidates the security properties of some crypto protocols if they only have been proven secure for sequential composition. So why did we want to support concurrent composition? Well, from an implementation point of view, it made it very, enforcing sequentiality turned out to be very awkward in the implementation. So it made our developers unhappy and also awkward for users of the system. You hand them access to one interactive mechanism, and then suddenly that's going to get shut off when they ask for access to another. It's also relevant for the practice that, in practice, if we are present in a number of data sets and people are setting up DP access to these data sets independently, there's no reason an attacker out there might, not, concurrently interact with these to try to learn something about us. Okay, and so through a series of papers over the last a few years, we have worked hard to extend, show that the composition theorems we knew for non-interactive DP actually extend to interactive DP for all of these flavors of differential privacy that I mentioned. It turns out that for some of them, they're very different proofs for the different kinds of privacy notions. And then in recent work, we've also extended to what are called odometers and filters, which is another kind of form of composition where the privacy, the epsilons, the privacy loss parameters can also be chosen adaptively. Since, for today, I haven't gotten enough into these notions for these open problems to make sense, but I just want to point out there are still some very interesting open theory questions here related to both of these results. Okay, so let me wrap up with just a few words of first about community. OpenDP really is, I've talked to try to focus on the research questions, but again, it's really a community effort. We have a very broad concept of what our community should be in OpenDP, not just the experts who are and users who are contributing directly to the software, but we want to find ways to engage even with the individuals in society or representatives of those individuals who are affected by the kinds of data releases and data sets that differential privacy is being applied on. There are lots of ways to engage with the community. So encourage anyone who's interested to join the community. And we really see it as an international community. And that was one of the motivations for the privacy workshop that Clement and I hosted last month, about a month ago. And it was really great to see the growing community here. So again, just want to encourage folks to join the OpenDP community, our Slack, our mailing list. And there's lots of ways to contribute, even if you're not an expert. Now, just to conclude the talk, I hope I've convinced you, or at least given you a taste, that differential privacy has raised fascinating questions, research questions. Some are theoretical questions, but actually also questions for law scholars and questions for people working in computer systems as well, while also being something that's transitioning to practice very quickly because it's addressing an urgent societal need. I've given some taste. This efforts to bring DP to practice, my experience has been, is that they just raise new research question after new research question. And these are, often just as intriguing as the research questions that we, come up on our own as researchers or theorists. One flavor of question that I think is important to highlight that I didn't bring up in this talk because it didn't somehow fit with the narrative are the statistical kind of questions. So I brought up research questions that really came up out of the effort to implement differential privacy in code. But there's also the questions that come up as you try to bring DP to statistical applications. And there's still a big gap between the things that we know how to do well in the differential privacy literature and the real needs of the data analysts, and the statisticians who work in various application domains like social science, economics, epidemiology, the kinds of things they need if they're really going to be making use of differential privacy. And so even things that are kind of stats 101 things like simple linear regression, we studied in some works, Clement and others have studied very simple hypothesis testing problems. We're still working hard to get a complete understanding of these questions. So there's kind of a gold mine here to be explored as well. Thank you.
For 11 now, I don't know if anyone has things, but I guess we can have one or two questions from the audience.
Can I ask a very naive question as a mathematician? Your definition of epsilon adjacency, I think it's called, epsilon DP closeness.
Yep.
Why do you use a multiplicative factor e to the epsilon? Because that's bigger than 1. And so you're going to have kind of a region in the right-hand side for which everything on the left will be satisfying that condition. So it's not really a constraint, so to speak.
Great. So these are bigger than 1 is what you want. So think of the e to the epsilon as like 1 plus epsilon, right? For small epsilon. And so we're saying for any particular output, the probability you get that output will be within a 1 plus minus epsilon factor on one data set and the other. So that is to say that those probabilities are close and their ratio should be close to 1. That's what the definition is.
Yes, but because the epsilon is bigger than 1, always for all positive epsilon, that's what I'm asking. I don't see the 1 minus epsilon constraint there.
Okay. The 1 minus epsilon is by symmetry. So since we quantify over all pairs of adjacent data sets, X and X prime, you can also switch. It also, when includes requiring the same for X and X prime switched. And so then you have the reverse one there. Thank you. Thank you.
We could take one more question and then we'll wrap up.
So do you think there's anything that is really missing in OpenDP that you think is really needed to be added to OpenDP in the next couple of years?
Do you mean in a software, from a
Yes.
software perspective? Oh yeah, there's a lot that needs to be there. So you know, it's taken us a few years to kind of really get the basic infrastructure done right. It's only in the last 6 months that we have actually these interactive, like the full support for these interactive mechanisms, the bindings for R and Python. A lot of the basic mechanisms are in there, but those are just the building blocks of interesting DP algorithms. And now it's ready for start filling up the library with all the interesting DP algorithms that are actually doing the end statistics that people care about. And that we've just gotten started on.
Also, when you started adding these things, and if you used your mathematical tools, did you find there was a lot of maybe unrealistic assumptions in the existing literature, or inconsistencies in models and things like that that was creating problems when you started to implement?
Yeah, there's a lot of stuff that as researchers and theorists, we sort of brush under the rugs in our papers, because sort of the human reading the proof is doing the debugging along the way. And so papers will be inconsistent on exactly which definition of adjacency. There are actually several definitions. Turns out, actually, and related to that, whether you treat the data set as ordered or unordered actually makes also a difference. But that's something we never talk about in our research papers. So I think it's more things that go unspecified, and then as you try to make it really precise, you now have to specify all these things, and then you have to find how to specify it in a consistent way when you want the components to actually interoperate.
Yes. Another question about the budget of the query. Yeah, you have a budget of queries, the number of queries, but except the numbers, and I mean, format the restrictions on the queries. Say some kind of questions you cannot ask, or you can, or the server only answer some special kind of question.
Oh yeah, great. So implicitly, yes, in the sense that the only kinds of queries you can ask are ones for which we have some kind of differentially private algorithm that can answer those queries to some reasonable accuracy, within some specified differential privacy budget. So in an implementation, it's like whatever you've managed to implement with differential privacy, your query space is going to be restricted to those. Now, in principle, it can be quite large and quite rich, and people have built, for example, compilers where someone can write a arbitrary SQL query, and then it gets translated into a differentially private form. And depending, for some natural SQL queries, you'll get a useful differentially private algorithm out, as long as you have enough budget to answer it. But for some, you might actually get something where it's just going to automatically introduce so much noise that you don't get anything useful out.
Thank you.
Yeah.
Ask one question. So currently the DB protects very well for each individual data items. But suppose, let's just try to understand the limitations of the DB mechanism. Suppose the data set actually differ at multiple data entry, but they differ at one set of data entries, and this set could be maybe quite large, let's say linear fraction. But let me share a common feature. Well, from adversary point of view, he only tried to learn whether this data set contains this special feature data or not. Would the DB still have any hope when this different set is large enough? Say,
yeah, great question. So it is possible, as I was saying, you're kind of one DP has what are called group privacy guarantees. So that as you go from differing, one individual, two individuals, three individuals, the privacy loss does degrade smoothly. But when you get to the regime where you're talking about, where it's a very large group, you start to either get very poor privacy guarantees or very poor utility. If you're talking about a scenario where you're interested in protecting a subpopulation that's really like as a group and not as individuals, that's like a linear fraction of the entire data set, differential privacy is generally going to be incompatible with that. And it won't let you, because it then starts to be kind of hard to distinguish between what you want to protect and what are sort of legitimate statistical questions about the population that you want to answer. So how do you distinguish those two? And differential privacy doesn't give you an answer. It will say something like that is, we consider that a question about the population, and we're going to allow that answer to be released. Or if you ask for group privacy at that level, you'll get no accuracy at all.
So that seems to be some inherently comparative.
Yes.
Okay, thanks everyone for joining the.
Thank you.